The introduction. My name is Joseph Andrews. I'm a third-year PhD student at Duke University, and today I'm going to be presenting on fully printed nanotube transistors and their application as pressure sensors with a focus on smart tire environments. For my talk today, I'll start by motivating the work with some larger trends in electrical engineering. Then I'll move to our printed fabrication, how we make these devices. Next, I'll show you how these devices operate under pressure. And finally, I'll talk about how we've integrated these devices with the material thickness sensor for fully smart tire environment. So a big trend in electrical engineering right now is the Internet of Things. It's predicted that by 2020, there will be over 20 billion devices connected to the Internet. In order to realize this huge advance, we're going to need low-cost, large-area electronics, and we think printed electronics is a way to realize this vision. So why printed electronics? For one, it's extremely low cost. So you're only using the material that you put down. It's a really high throughput process, so you could use it for manufacturing. And lastly, it's substrate agnostic. And this is really good if you're looking to do flexible electronics, stretchable electronics, or even large area electronics that wouldn't be able to fit in traditional electrical fabrication vacuum systems. So in this work, we do printed transistors. You might be wondering why we do printed transistors. For one, there's different voltage knobs that we can turn to amplify the signal. There's a well-understood baseline, so we can see if the transistor is turning off and on, we know that the sensor is still operational to a certain extent. You can also use the same device fabrication for the signal analysis and communication. And lastly, printed fabrication, again, is low cost and also may allow us to do future arrays to do mapping, sensing mapping. And the physical parameter that we're looking at in this work is environmental pressure. So this is a little bit different than tactile pressure. The range that you're interested in may change. And for this work specifically, we're looking at automobile tires. So all the work is done within that range of automobile tires. So before I get into how we fabricate the specific devices, I wanted to give a quick overview of aerosol jet printing. It's similar to inkjet printing, but it's a method that allows you to use a wider variety of inks and allows for resolutions that are a little bit lower. So basically what we do is we start by dispersing nanomaterials within a solvent. Then we ultrasonically excite that ink into an aerosol, similar to like a hairspray. And then next we take a carrier gas, we pick up that aerosol and take it to the deposition head. And this is where it gets a little bit interesting. You see we have an inert gas stream that's then inputted into the deposition head, flows annularly around the stream that contains the ink aerosol. And what this does is it protects the deposition head from clogging. And this allows us to print nanomaterials, which traditionally like to clog to a lot of different nozzles. So we can do long-term continuous printing. And it also guides the ink down to the substrate, which gives us resolution down to about 10 micrometers or so. And with this printing process, there's also a bunch of different parameters that we can change to optimize different inks. So we can change that sheath gas flow rate, that atomizer gas flow rate, or even the ultrasonic energy that excites the ink to give us different properties. So for these devices specifically, we start with either a glass or a Kapton substrate. We clean and plasma ash it to prepare for the ink deposition. And these are backgated transistor devices. So first we need a conducting backgate. And so for that, we use silver nanoparticle ink. These are particles about size of 30 to 50 nanometers. And we print them and then we center at 200 degrees C. And what that does is it merges the nanoparticles to form a continuous conducting film. Next, we printed our dielectric. This is a commercially available dielectric from Xerox, PVP PMSSQ. And so we can print that dielectric and then we cure it at 80 degrees C on a hot plate and then 140 degrees C in an oven to cross-link the polymer. Next is the semiconductor. For the semiconductor, we use semiconducting carbon nanotubes. They were purchased from Nano Integris. They have 99.9% purity, semiconducting purity. And we print those, and then we rinse with toluene, and that's to remove any leftover surfactant. And then finally, we anneal it to remove any excess solvent. And lastly, we print the silver source and drain, exactly how we printed the silver backgate. So now we have all of our transistor components, and all of them are fully printed. So here's a snapshot of what the device looks like. We have the full structure as well as a photograph of the transistor itself. The big silver nanoparticle things you see in the photo on the bottom left are just to make it a little bit easier to contact. The actual device area, the device length is 150 microns, The device width is 500 microns, and the dielectric square that I printed was 1 millimeter by 1 millimeter. In the bottom right corner, you can see a few SEM images of what the carbon nanotube film looks like, as well as what the silver nanoparticle continuous films look like. And here's what the transistors look like, not under pressure, so just in open air. So carbon nanotube transistors, they're Schottky barrier devices, so they're not intrinsically, or they're not doped N or P-type. It's an intrinsic channel where the behavior is determined by the work function of the metal contacts. And so these show P-type behavior, which is pretty typical for carbon nanotube transistor. It's a little more difficult to get N-type behavior. And they have an on-off ratio of 10 to the 4 and an on current of 3.2 microamps per millimeter, which is about average for printed nanomaterial transistors. Now I'll move on to testing these transistors under pressure. So we had a custom designed pressure chamber built that allows triax input, so we can do really low noise signal measurements on our transistors. Has a digital gauge, so we can know the exact pressure, as well as temperature control for the stage. And the operating range is 0 to 80 psi. For this work, I do use pounds per square inch because in the US, the tire industry, that's all they use. But just to give you a conversion factor, the maximum I use is 42 psi, and that converts to about 300 kilopascals. So if you're looking at my plots, the maximum is 300, the minimum is 0 if you're more used to kilopascals. And so for the test details themselves, so I start the chamber at 42 psi with the sensor inside. I let it stabilize for 3 minutes, and then I do a transistor sweep from 30 to negative 30, and I do a full hysteresis sweep just to make sure that the transistors are all starting in the same initial condition. And so here are the initial transistor results at various pressures. And the most obvious thing is just the decrease in the on current. So you can see the higher pressure is the dark blue, and it goes all the way down to that light purple. But just looking at this, it's hard to see exactly what's going on, so we pulled out more specific electric parameters. The first one that we pulled out is the on current, and this is not the on current at an overdrive voltage. This is just the on current at a specific gate source voltage and drain source voltage. And what we see is increasing, looks fairly linear for the first part of the pressure, and then exponentially increases. But this is a composite of two different electric parameters, the threshold voltage when the device is turning on, as well as the transconductance. So we pulled those out separately. The threshold voltage has a similar look and increase exponential with pressure. But if you remember, we started our test at 42 psi and ramped down to 0. And the decrease as the number of tests you see is pretty common when you're sweeping a transistor over and over, that threshold voltage will reach an equilibrium. So we think that this is not due to pressure, that it's due to threshold voltage, and that it's due to threshold voltage equilibrium, and we could see that as we did hysteretic sweeps. So the parameter that we did see is sensitive to pressure is the transconductance, and this is fairly linear over this range. And what we see is a change of 48.1 picosiemens per psi, and an R squared value of 0.98 for the linearity. There's some hysteretic effects with this parameter. We're still working on this. I don't have those results here, but it's the parameter with the least amount of hysteretic effects. And we find that it decreases as you cycle it through pressure cycles. So the mechanisms of how this sensing is working, we have a few different things that we'd like to postulate, to hypothesize. We think maybe the tube-to-tube resistance within that network is being modulated. They are top contact resistance, so another thing that could contribute is the contact resistance is being modulated with increasing pressure. And lastly, the dielectric is fairly new and hasn't been printed that often, so we're not sure of the properties of it. They might be changing under pressure, giving us better electrostatic control at higher pressures. So from here, we designed a proof of concept test just to show that we could measure this signal and transmit this signal using an Arduino, low-cost Arduino and Bluetooth module. So we designed a simple voltage divider circuit with our transistor as one element, and we measured the conductance of the carbon nanotube thin film at a specific gate source voltage and drain source voltage, and correlated that to pressure. So the whole design fit inside the pressure chamber and communicated the data back out to a cell phone. So this data that you see here was all onto a cell phone. Basically, as a proof of concept that this pressure sensor could be fully encapsulated in the tire and give the end user the data on the outside. Here's a little data of how the sensor works over time. So you see that the conductance saturates after about 60 to 90 seconds. So it's not quite immediate. There's some equilibrium time. So our lab has also done a lot of work developing a material thickness sensor that we plan to use as a tread depth sensor in tires. This was some work that we published over the summer. And basically, this is another fully printed device. It's 2 printed electrodes that are printed adjacently, and an electric field is applied between those electrodes. A lot of that electric field is lost directly between the electrodes, but some of it extends out of plane and is perturbed by the overlying material. And that perturbation depends on that material's thickness, and we can use that to actually back out the added rubber thickness. So this sensor is placed underneath a tire, and rubber plies are added, and we see a fairly linear change in the signal reflectance between those two electrodes. And so our goal is to integrate these 2 sensors together, put them on a large Kapton substrate, which is flexible and then could be inputted inside of the tire. And this would give us a lot more data than we have currently within tires. Currently, usually just have a singular pressure or temperature sensor. What this would do is it would map the tread of your tire as well as tell you information about different pressure differentials. And because it's printed electronics, it's low cost, so it could be fairly ubiquitous in the tire market. So here are the conclusions. We developed a fully printed environmental pressure sensor. We've established that transconductance is the most sensitive parameter, shown a proof of concept design with the Arduino and Bluetooth, and also postulate that we could integrate this with a material thickness sensor for a fully smart tire system. For future work, we need to do a lot more work on identifying the mechanisms. And so we plan to do this by designing structures in which we could extract the contact and the sheet resistance by printing multiple channel links and using transmission line models to extract those values to really gain more understanding. Is it the sheet resistance that's changing, the contact resistance, or that electrostatic control that's based on the dielectric? So that's the future work. We also plan to look at different geometries and further explore the hysteretic effects. I'd like to thank especially my advisor, Dr. Aaron Franklin, Dr. Martin Brook, another professor at Duke who advised me on this work, my colleagues, my research group for their collaboration and support, and financial support from Fetch Networks, a small company in North Carolina. I have my email up here if you have further questions, but I'd love to answer a few right now. Thank you for your attention.